Hello guys, welcome back. In our last video, we've introduced several key functions in the apply family, including lapply, sapply, and mapply. These functions allow us to vectorize arbitrary functions that do not support vector arguments originally. In this video, we are going to introduce two more members in the apply family and discuss how to use loop functions to implement a common data analysis paradigm called the split apply combine paradigm. Now let's start with the apply function that works with arrays. Suppose we have a 2x4 matrix and want to calculate, say, the means of all its rows or all its columns. If we simply use lapply or sapply, we'll end up with the same number of elements and nothing has been aggregated. This is because lapply and sapply treat this matrix as though it were a vector. In this case, we need to use another loop function, apply, short for array apply, which allows us to evaluate a function over the margins of an array. Since matrices are two-dimensional arrays, we can use it here. So how does it work? As you can see from its parameter list, the first parameter is used to specify an array or a matrix. The second parameter, margin, expects an integer vector that indicates which margin should be returned in the result. And the last important thing we need to specify is a function that we want to apply to each of the margins. Then, as usual, we have this special parameter used for other arguments that we want to pass to this function. Now I can use the apply function on this matrix. I give it the margin 2, which indicates the column dimension, and I pass the function min. And so what happens is I get back a vector of length 4 that has the min of each of the columns of this matrix. So when you apply min over the matrix, the second dimension, which is the columns, is returned, while the other dimension, which is the rows, is collapsed. So the idea is that we are taking the min across all the rows in each column, and as a result, the row dimension has been eliminated. So we get this vector, which has the min for each of the columns. Similarly, we can calculate summary statistics for all the rows of a matrix or an array. In the second example, I call the apply function on the matrix M again, but this time I supply it the margin 1, which means preserve all the rows but collapse all the columns. And here I'm calculating the sum of each of the rows. As a result, I get a vector of length 2. Because there are 2 rows, and inside each row, I calculate the sum across all the columns, making the column dimension eliminated from the result. Apply allows us to apply an arbitrary function over the margins of an array. But for simple operations, like calculating the sum or calculating the min of a column or a row, there are special functions that are highly optimized to do this very quickly. So for calculating the row sums and row mins, there are functions row sum and row mins. And similarly, there are column sums and column mins, which do the same things for the columns. These are equivalent to using the apply function, but they are much faster because they are optimized to do those operations specifically. So if you want to calculate the sum or the mean of a column or row of a matrix, use these functions instead. And this slide shows other ways of using the apply function. Suppose I want to go through each row of the matrix and calculate the first and third quartiles of that row. Here I need to use the quantile function. Now the quantile function needs the quantiles that we want to calculate. Actually, there's no default value for that. So I have to pass the percentiles to the quantile function through the ellipsis parameter of apply. Here the argument for quantile is called probabilities, and I give it 0.25 and 0.75, meaning I want to calculate the first and third quartiles. And I set margin to 1, meaning that I want to preserve the rows. So what this code does is, it goes through each row of the matrix, and for each row, it calculates the 25th and 75th percentiles. And for each row, there are going to be two numbers that are returned. And the apply function creates a matrix that has two rows, and the number of columns equal to the number of rows in this matrix. So this matrix stores the 25th and 75th percentiles of each row. Next, suppose I have more than just a matrix. Suppose I have an array that I want to do something with. Here I create an array, and it has two rows and two columns, and the third dimension is 10. And we can think of the resulting array as 10 2x2 matrices, which are stacked together. What if we want to take the average of these 10 2x2 matrices? And the average of a bunch of 2x2 matrices is going to be another 2x2 matrix. And so I can call apply on this array. To keep the first and second dimensions, but collapse the third dimension. So here I specify margin to 1 and 2, meaning that I want to preserve the first two dimensions and collapse the third one. And what this call will do is, it will take the array and average over the third dimension and give me this mean matrix. And this is what I would like to introduce about the apply function. Next, I'm going to show you how we can use loop functions to address a really common problem when we investigate data. Suppose we have a couple of scores of 3 distinct players on some computer game, and the data is organized in this data frame. Suppose we are interested in calculating the average scores of these 3 players. So how can we divide the data on scores into 3 groups by players and then calculate their average scores? Theoretically, we need to go through several steps to accomplish a task of this type. That is, first split data into groups divided by some grouping variables. Then apply some common operations over all resulting groups independently. And finally, combine all group-wise results for presentation. These steps are collectively referred to as the split, apply, combine workflow for data analysis. And one way to implement this workflow in R involves applications of the loop functions. Specifically, in the data splitting step, we can first use a very handy function called split, which allows us to split up rows of a data frame according to a factor variable. Although split is not a loop function, it is heavily used in conjunction with functions like lapply and sapply in this kind of data analysis problems. So the split function takes an object x, which can be either a vector or a data frame. Then it splits the values in this vector or rows in this data frame into the number of groups that are identified by the second argument, which is a factor of the same length. In this example, the second column contains a factor that has 3 levels, or 3 distinct labels. That is the names of the 3 players. It identifies which group each element in the first vector should be assigned. So the score values are split into 3 groups and organized in a named list. Once we've gotten those groups split apart, we can use lapply to apply the needed function to those individual groups, and then use onList to present the results in a compact form. Of course, we can condense the apply and combine steps into one by using sapply. Alternatively, as I mentioned, split can also work with data frames. So we can split up the rows of this data frame first and specify the variables to be summarized later by using an anonymous function, as demonstrated here. After knowing the basic use of the split function, let's consider a more complex problem to explore its full potential. This Enron emails dataset contains a tiny portion of the daily emails sent among Enron's senior management over a certain period before its bankruptcy. And it is these emails that brought down Enron and shaped new standards in the business world. In this data frame, the from and to columns contains the employee IDs for a pair of senders and receivers, and the N column contains a count of daily email exchanges between the corresponding pairs of senders and receivers. Suppose we want to quantify the intensity of email exchanges between any pair of employees in this dataset. We can use the split function to split up the rows according to the combination of the from factor and the to factor. Because there are too many combinations to be listed in a limited amount of space, R only gives a truncated view of this result. But it already lets you see clearly that many of the resulting groups are empty, meaning that not every employee sent emails to every other employee in this period. So with multiple factors and many levels, creating an interaction can result in many levels that are empty. And these interaction levels are not very useful for our subsequent analysis. Actually, we can drop those empty levels from the output by simply setting this drop option to true, as shown here. Then there will be no empty groups anymore. So far, we've seen several examples of the split apply combine workflow in action. This slide gives a summary of the steps that make up it. Because split apply combine is such a common paradigm in data analysis, We really need something easier, something that consolidates these steps into a single one and allows for less typing. Actually, there's another important apply function to which we can resort for this purpose. That is tapply. Tapply allows us to group the elements of a vector and apply a function over the resulted subsets. Here I show how the 3 steps in the previous example can be condensed into a single call to the tapply function. Like split, tapply takes the vector to split as the first argument, and a factor that identifies group as the second argument, then followed by the function to be applied, and then the ellipsis parameter used to capture other arguments that may go to this function. And here the simplified keyword is used to indicate whether we want to simplify the results, kind of like the sapply simplification. Actually, we can think of tapply as a combination of split and sapply, as shown by this custom implementation. But tapply has one drawback that makes it not an exact equivalent to the combination of split and sapply. That is, its first argument can only be vectors. So don't supply a whole data frame directly to tapply. And this slide gives you the result of using the tapply function for the Enron email example. After learning both function closures and loop functions in R, perhaps it is a good place to summarize an important feature in R or in any functional programming language. That is the use of higher order functions. A higher order function is a function that does at least one of the following. It can be a function that returns a function as its result, like what we've seen in examples of function closures or function factories. It can also be a function that takes one or more functions as its arguments. Actually, we have a specific term to refer to functions of this type, functionals. Because R's functionals allow us to use another function to express the exact procedure we want to apply. By using them, we can better communicate our intent in coding and make our code less error-prone. So in R, we should use loop functions over explicit loops as much as possible, as they lead to cleaner and easier to read code. Besides, apply functions can be faster than for loops, sometimes dramatically. As we've seen, one important application of base R loop functions is to implement the split, apply, combine data analysis paradigm. While they get the job done, their syntax are not very consistent because these functions have grown organically over time and were written by different authors. For example, in tapply and sapply, the parameter that controls result simplification is written like this, while the same parameter in mapply is written like this. This kind of inconsistency makes learning and applying these functions challenging, as you have to memorize all of variations. Besides, these functions cover only a partial set of all possible combinations of input and output types. For example, if we want to perform some analysis on a data frame and expects the result to be returned in a data frame. It can never be the case, as a majority of these functions can only output vectors and lists, requiring us to do additional work for data transformation. To address these drawbacks, over the years, several alternatives have emerged and aim to provide a simpler and more consistent syntax to operationalize the split, apply, combine data analysis paradigm. So next, I would like to give a quick introduction to one of these alternatives, the plier package. The name plier here is given to invoke pliers. The plier package gives us control over the input and output formats and keeps the syntax consistent across all variations. So it allows us to smoothly apply the split, apply, combine strategy. Moreover, it also adds some useful features like error processing, parallel processing, and progress bars. But since we'll introduce a more sophisticated and data frame-focused package called dplier, which is perceived as the next iteration of plier in the next unit. Here we only highlight some basics of plier. The basic naming of the plier functions includes two letters followed by ply, with the first letter referring to the input data format and the second to the output data format. And there are three main letters, D, A, and L, referring to these three main formats for inputs and outputs. So the name ddply means take a data frame, split it up, do something to it, and return a data frame. After loading the plier library, we can first take a look at different parameters of ddply. Among them, this variables parameter is used to specify the combination of variables to split by, and it supports various specification syntax. Let's apply the ddply function to the unroam email data to see how it actually works. Because the ddply function only works with data frames, so it takes the data frame as a first argument. Then, a combination of variables in that data frame as a second argument to specify by which we want to split that data frame. The third argument is a function named summarize. It is also provided by the plier package and works as a procedural argument to the ddply function. And basically it means we're going to summarize these resulting groups, possibly in terms of multiple statistics. And the following named arguments, which will be passed on to the summarize function, indicate the type of summary statistics the summarize function should produce. Here we require the summarize function to produce both group-wise sums and group-wise means, all at once. And the result is going to be stored in a new data frame, which includes colons for these two grouping variables, as well as those for these two summary statistics. As you may find, the colons for these two summary statistics are labeled by these two keywords, respectively. The summarize function creates a new data frame. But if you want to modify the existing data frame in place, we should instead use the mutate function. Here, I specify three transformations to create three new variables based on the n colon. As a result, 3 new colons are added to the existing data frame. And these missing values are introduced because their corresponding groups contain only one observation, on which the standard deviation is not well defined. And if you take a closer look at these transformations, you may find the third transformation that normalizes the data actually relies on the results of the former 2 transformations. So it suggests that these transformations are executed iteratively so that later transformations can use the colons created by earlier ones. All right, that's all I want to introduce about the plier package. Actually, the plier package is a very easy to use package for data wrangling, and you are highly encouraged to explore it in your spare time. And next time, we'll introduce several more sophisticated data wrangling packages belonging to the so-called tidyverse collection.